Yeah, good.
Okay, great. Yeah, thank you. So tonight I'm going to be talking with you about a recent piece of research that was published just this past fall in Nature Communications. So everything that I'm going to discuss with you tonight generally relates to that publication, but there's some material at the end that I'll discuss that we're pursuing presently. And this work's being done with a variety of collaborators, mainly from North America and Europe. And I'd like to thank our funding sources, the Polar Continental Shelf Program, NSERC, the Academy of Finland, and my university, Simon Fraser University. The title of tonight's talk is Channelization of an Arid Permafrost Landscape, Observations and Synthesis. The talk has 4 parts. I'm going to try to motivate the talk with some general background to get everyone oriented to the ideas that we are interested in. Then I will review quickly our field site on Axel Heiberg Island. Then I will review some observations that are pertinent to the questions we're trying to address presently. And then I'll try to synthesize some information to provide a foundation for looking ahead where we hope to go, say, in the next 5 to 10 years with our research. So to set the problem up, we're really focused on one basic question, and that is, how does polygonal ground or polygon fields influence surface water routing and channel network development? I think these visuals provide a decent way to bring this question to life a little more. On the left-hand side here, we have a valley floor that has polygons on it, and these polygons are in various states of degradation. And flow in the picture is from right to left. This picture is from Axel Heiberg. And basically what we want to try to understand is, how do we go from a setting where the conditions look like this, where the polygons are a bit more passive in collecting water seasonally as the ground thaws and the permafrost thaws, to something that looks more like we see on the right-hand sides. At the top is a smaller scale example. In general, what we're interested in is, how do we go from polygonal ground on valley floors to stream channels? A small stream channel, possibly like this, which is roughly 3 meters across, or to a valley system a little larger, where the alluvial corridor is approximately, say in this picture, 25 meters. And this picture is pretty interesting because you can see that polygons are still present on the valley margins here, and they likely had some semblance to this motivational picture here, where at some point in the past, they were more passive features, and then over time, it's evolved into an alluvial corridor. So we want to understand how we go from polygons to river channels in general. Of course, there's been quite a bit of research in the last 20 years, primarily on questions related to this. Here's an example, a very prominent example from Bylot Island, south of Axel Heiberg, published by Fortier and others. And they documented the evolution of what they called a gully system through a polygon field over the course of several seasons. And this folded into PhD work by Etienne Gaudin, where he went out and actually collected the information to characterize this a bit more. This is a classic case where what they propose is there's primarily thermal erosion along ice wedge boundaries that then evolve over time through ground collapse into this interconnected gully system. Another example is from the opposite side of the planet in Antarctica, in the dry valleys. And this is work done by Joe Levy and his colleagues from about 2005 to 2010. And what their work shows, similar to the Fortier work, is how polygons can play a role of interconnecting between different developing gully systems and evolve into say, a gully system that transmits water, conveys water seasonally, probably with some sediment transport. But in both cases, the systems that the authors were reporting on are quite contained and don't really scale up to the watershed scale. And that's what we put forward primarily with our observations recently. And then last, a bit more interesting from a sort of solar system perspective, is we can see conditions similar to those reported in the Arctic and Antarctica having played a role in shaping the Martian surface. This is work from Christensen and Hopler in the 1980s. It's buried in a NASA annual report. These reports are very large, 500 pages. This report covers roughly 5 pages. And basically what they proposed is that a impactor, oops, sorry about that, an impactor created this crater, this flash melted ice that was in the sort of near ground region, releasing large volumes of water that then flowed along topographic gradients and apparently along interconnected polygon troughs to create this channel system that's quite large on the scale of 200 kilometers. So in general, we have this background research that gives us a good sense that yes, polygons are important for surface water flow, and they can evolve into these interconnected gully systems or perhaps even a channel system. And our goal is to examine that question in a bit more detail. More recent work has pointed a bit more directly into some of the issues that come up when we start thinking about this problem. First off is that the difficulty of the problem really is set by sediment transport. And in this review by Teneneev and Latsari in 2022, when they think about erosional networks, a couple things come to mind. One is that the relative importance of permafrost controls and the development of erosional networks is relatively significant with respect to estuaries and river valleys. And really the problem boils around thermal interactions as erosional networks develop, and also the availability of water to drive the development of these erosional networks. And then a more recent a review released the same year by Zhang et al. Kind of focused in the problem on two aspects, and one is sediment availability, how coarse sediment, primarily, not fine sediment, so say sands, gravels, cobbles, things even larger than that, how those become available in the landscape that then also play a role in setting the sediment transport capacity of these developing erosional networks. And this vision or this view of the problem is starting to bring a more temperate view of rivers into Arctic or permafrost settings in the Arctic, Antarctica, as well as high elevation regions. Teneneev and Latsari they have a sentence in their review that I think summarizes the problem quite well that we directly try to address now, and through some PhD research are taking that forward. And that simply is, if we have features that are initiated through fluvial action, so erosional channel networks, for example, that their evolution is constrained by permafrost, and they are constrained by the evolution through both mechanical and thermal erosion. And what we'll talk about in a few minutes is the thermal erosion part from a river's perspective is really the piece that's missing and preventing us from making progress. Of course, this problem has widespread importance, primarily through what we're seeing today with Arctic amplification of air temperatures in the Arctic. This is a plot from our publication, and I've worked with CREW-TEM5 data to produce this plot. And basically what we see is roughly from about the 2000s onwards, we're starting to see at 55 degrees north latitude in the Western Hemisphere, so all stations north of 55 degrees, a roughly 2-time rate difference between how fast temperatures are warming globally versus how quickly they are warming in the Western Hemisphere north of 55 degrees. And if we look at the 75th percentile of the population, it's a 4 times rate difference. So air temperatures are amplified in the Arctic due to a number of effects. And this really has implications for a number of things that relate to erosional channel network development. A couple examples of issues that come to bear some importance as air temperatures in the Arctic warm. One is active layer thaw to greater depths. Here's some recent data published just this month by Liu et al. And essentially what we're seeing with these red colors is increasing active layer thickness trends per year that are positive. So the active layer thickness is getting thicker as we go through, as we go on in time. This is principally has the effect of, say, releasing more water seasonally to erosional channel networks, and then creating a greater storage space at the end of the melt and thaw season for the subsequent season's water budget to fill the pore spaces. This also leads to increasing rates of landscape disturbance. Here's an example from Axel Heiberg. This is a large failure event that occurred like the week before we arrived on Axel Heiberg. These types of events are large. This one measures roughly 300 to 400 meters in width, and it created this erosional channel that connected all the way down to the main valley floor, effectively creating the seed of a new tributary basin, if you will. And then last example would be increasing fluxes of water and sediment from permafrost regions. Here's some results from Lee et al. Published in 2021. And essentially, the red dots tell you in this latter period during their observational record that we're seeing more water released to the Tibetan Plateau as well as more suspended sediment. So this amplification of air temperatures in the Arctic, as well as increasing air temperatures in high elevation regions, has many different environmental implications. All of these play an important role in the development of new channel networks. And one of the main implications of this is widespread and rapid landscape change. And this is what our work partly documents on Axel Heiberg. And then through subsequent field seasons, we're starting to document similar effects on Devon Island as well. So it's sort of to set the technical problem with the development of erosional channel networks and thinking about polygons. One of the questions that comes to mind is how might polygons influence landscape change, and in particular within mountainous terrain like we have on Axel Heiberg and parts of Devon Island. One of the obvious examples is that polygons change local topographic gradients. It's clear in this photograph in the regions where polygons occur on the hill slope here or down on in the main valley floor that we have a roughly 1 to 1.5 meter change in topography as we move, say, across a polygon into a trough and into another polygon. These topographic differences across the landscape here will affect how water on the surface flows across it, how it organizes, how it coalesces, etc. All of these play an importance in the development of erosional channel networks. Polygons and their troughs also can offer pathways for surface water and even shallow surface water as water moves along topographic gradients. And this photograph provides any number of different examples of how these pathways can develop in time. So we'd like to take all of these sort of basic ideas and motivating observations and develop just a few hypotheses that really grow from the work that's been done to date and supported by the observations we made on Axel Heiberg. And the first hypothesis is that polygons spatially organize surface flows. Here's a cross-section hypothetical across a polygon field. We can see a primary trough, perhaps in a secondary trough. In this case, I've shown coarse particles on the trough, on the bottom of the trough, and various water stages can occur within the troughs as the melt and the thaw season unfolds. This will clearly have an impact on then how water organizes within the polygon field and under topographic gradients, say down a valley, how that water moves or is routed through the polygon fields. And that can cause differences, say, in sediment supply, or I'm sorry, sediment that's carried by the water as an input, and a difference as we come out, say, at the bottom of a polygon field as an output, because there could be deposition as water is flowing through this polygon field. Just the basic action of how an alluvial channel or a channel in a more temperate climate works. This in cross section, we can look at this in a little more detail. In a primary polygon trough, perhaps at some point in the more recent past, say 100, 1,000 years ago, as the polygon was forming, this might have been the surface at that time in the trough. As time goes on, that trough becomes more pronounced. And at that point, or at some point, the trough may encounter coarse particles. And then these coarse particles will interact with how the polygon trough evolves in the future based on how surface water flows through it or is routed through it. This becomes really a case of, we believe that channelization with through water routing within polygon troughs can change the rate at which the landscape evolves. And in this simple plot here, with rate on the y-axis and time on the x-axis, increasing both to the right and up, essentially the polygons will increase the rate at which the landscape is changing, or how we can observe the landscape to change through measurements, which is the case where perhaps we have no polygons. And essentially the reason is because polygons can help organize surface flows, thereby enhancing erosion in specific parts of the valley floor, for example. This is also clearly dependent on the sequence and timing of seasonal flood events. Here I've just drawn a fictitious flood, say in late May, and another one in July. Looking out into the future as climate change continues to unfold, and we see differences and changes in trends within the Arctic and high elevation regions in terms of precipitation intensity, heat waves, etc. How these future seasonal floods occur has a role in how erosional channel networks develops, because at a very general level, the magnitude of the floods and their duration really sets how much work can be done to the landscape. Now, to make progress on this problem, it requires us to have a generalized way to predict bedload transport, say for frozen. Okay, sorry about that. To make progress on the problem requires us to have an ability to, say, predict or calculate bedload transport for frozen or partially frozen substrate. If you think back to the image I showed you in the first slide, some of the smaller streams and rivers in the Arctic, for example, they go dry or nearly so by season's end. So it's very possible to completely freeze the substrate, and that frozen condition will play a role as the melt season unfolds in terms of how polygons can influence the rate at which the landscape modifies. Now this problem is made a little more difficult by the fact that a lot of the Arctic in Canada is a polar desert climate. In particular, where we worked right here on Axel Heiberg, we're looking at annual precipitation totals of less than 100 millimeters. It's just not that much water to do work to the landscape to drive the development of these erosional channel networks. So the loss of permafrost through increased air temperatures, how much ice exists in the subsurface pore spaces within the active layer, how much water volume in total occurs in a given season, all of these wrap up and help to frame how much polygons can influence the rate of erosional channel networks. And really at this point, what we're missing is how we can take this information and make a prediction, for example, of bedload transport, because that's what matters for alluvial rivers. Okay. That's the basic problem setup. I'll now step you through our field site on Axel Heiberg. So yeah, we were working up on Axel Heiberg Island. Basically, our field camp was roughly right here where my mouse is, and we covered the entire eastern side of the island off the ice cap from, say, in this region here. We also made it over to the west side of the island and did work in polygon fields over here. This is the particular valley that we worked in that's reported in the publication. We gave it the name Muskox Valley because of a lone muskox that we encountered in the valley at the time of our field work. This view is looking towards the west at a part of the Muller ice cap. The valley itself is headed roughly by this glacial lake that you can see at the top of the image, and then water flows down valley in this direction for roughly 7 to 8 kilometers before it joins up with this main river trunk system and heads out to the Arctic Ocean, dumping in about right here. You can see in the valley floor this strong polygonal pattern that essentially occurs from the photograph bottom all the way up to the lake system itself. There's also plenty of solifluction lobes and other periglacial landforms you'd expect to find in an environment like this. This valley was ice covered during the last glacial maximum, not surprising. Deglaciation is thought to have occurred in this region roughly starting about 8 to 10,000 years ago. Muskox Valley itself, we speculate, represented a subglacial channel from when the Muller ice cap covered the valley floor. And when you walk along the valley floor and you inspect the channel walls, in some sections of the polygons themselves, you can see ample coarse material that's evidence of a sort of subglacial channel system. This material is imbricated, so the grains are resting on one another. They're quite rounded, indicating transport over distances sufficient to wear away their angular edges and so forth. Sort of the classic alluvial deposit that one might expect. As I said, solifluction lobes are widespread, and to us that sort of indicates that permafrost thaw is active under the presently warming climate. And as I said, the climate here is a polar desert climate. As best we can tell, noting the closest climate station is roughly 50 kilometers away, 80 kilometers away. It's about 70 to 80 millimeters a year precipitation. Mean annual air temperature here is about negative 19 degrees Celsius. Just some example photographs. I'll show some more in a minute of what the valley floor itself looks like, but I just wanted to draw your attention to three things that I think are relevant and important. First is this sort of alternating pattern of polygonized areas with a channel cutting through the polygon troughs next to these wetland areas where the polygons themselves, it's very difficult to tell if they are there. They could be buried, but essentially from sort of a sedimentological perspective or thinking about how river valleys evolve in time from an immature state to a more mature state, we're seeing the valley floor itself be regraded presently through the action of erosion, and this might represent an erosional source zone, and this could represent a depositional zone. Just the sediment eroded here as the channel network is developing could have been deposited right here, creating this wetland. Along the valley margins in areas like this, where we saw polygons, it's common to see tundra moss growing in the walls of the polygons themselves, indicating to us that the polygons have shut off. They're no longer active. As we know, moss can take anywhere from, say, half a century to a century, perhaps, to grow. I'm not an expert in this, but speaking with a few ecologists, these were the timescales that I was told. And then a different channel section, just wanted to show this because it clearly provides an example that this is an evolving sort of more alluvial channel environment where we have active bedload transport either occurring in the recent past or occurring, say, roughly on the seasonal timescale. So the implication of some just basic observations from the study site in Muskox Valley is that the water budget for channel creation today in Muskox Valley mainly sits in the lake at the head of the valley, in permafrost and how it thaws seasonally, the melting of ground ice and the volume of that ground ice that's available for melting, with also contributions from seasonal snowfall. And, like any windy mountainous environment, snowdrifts can be an important local source of water well into the summer and even through the fall season up until the next winter. Okay, so moving on to observations. The principal data source that we collected during our time there, we spent only one day in the field in Axel Heiberg. I don't know how familiar folks are with field work done in these high Arctic settings, but commonly you go out in large teams and essentially you take all of the research objectives for the team and you divvy them up over the days of the trip. And then essentially everyone contributes to addressing those research objectives. So when we laid out our 2019 field season, That gave us 1 day to explore Muskox Valley. And during that day, we collected LiDAR with this mobile backpack scanning system developed by this engineer, Dr. Antero Kuko, who is a member of our team. Antero designed and built both the electronics, the software, and the hardware of the mobile scanning system. Essentially carry it on your back and you walk up and down the valley floor, say in a zigzagging fashion. As you go along, the data is being processed in real time, so you can see a picture of the coverage and where gaps may be. So when you get down to the, say, bottom of the valley floor, in this case, you might want to turn around and head right back up. What I'm showing you here is a hillshade of the resulting topographic surface that we calculated with the LiDAR data. And this would be some of the raw ground reflections that we collected with the mobile scanning system. And clearly you can see its polygons occur at many places along the roughly 2.1 kilometers valley floor where we collected the data. And then these polygon regions are interspersed with these regions where polygons are not really well expressed, and we sort of characterize them, as I said, as these sort of wetland type environments because there was standing water, there was emergent seasonal vegetation. Some more photographs of what these different sections of the valley floor where we collected data look like. So here we have a prominent channel system starting to develop, and it really is bisecting between adjacent polygons on the valley floor. Here we have the distal end of that developing channel system heading out into this wetland type environment. Here's a very nice expression of channelization through a polygon field. And here we have quite a few polygons that are now just starting to be dissected and interconnected through polygon troughs with seasonal flows. Some cross sections for 3 areas along here. We have both what I would call single threaded channel system. So this is at the top of the valley close to the lake where we have this clear low point. The channel is roughly 4 meters deep. It's bedded in gravels and cobbles, and there's active slumping and failures on the sidewalls. We also have a section where we have a multi-channel system where flows can move along different polygon troughs that sit adjacent to each other on the valley floor. And then in these wetland regions, we can have virtually very little topographic expression across the valley floor, say over 30 to 40 meters in width. We calculated the power spectra of the topographic data, both in a down valley sense, so in this direction, and also across the valley in this direction. When we calculated the spectra down valley, it's many different parallel lines going across the bottom of the valley floor. And when it's across valley, it's again a number of parallel lines in a close association to calculate their spectra. Basically what we learned from looking at the power spectra is that most of the polygons in Muskox Valley have this dominant wavelength of, say, order 10 meters, both in the down valley and in the cross valley direction. And this despite the fact that the valley is actively sort of reorganizing based on past flows into this nascent channel network. And we can also look at a profile running down the say the lowest point along the valley floor. So in this channelized section, the profile moves along the bottom of this very clear channel. As we move into the wetland section, I follow the lowest elevation that's connected, and so forth and so on. What we see is along the valley floor, slopes range from roughly 9% to about 1%. And we also calculated a width to depth ratio. The width to depth ratios range from roughly 100 to about 5. And the width to depth ratios, we're looking at the active valley width and the height at the deepest point within that width. And basically what we learned from looking at this information is even though we have this channelizing valley system with clear sections that are channelizing and sections that aren't obviously channelizing, we don't see a big difference in the local slope, despite these two contrasting characteristics. The only thing that we see that provides perhaps some clue of how the system is evolving with the warming air temperatures is wherever we see tributaries entering the valley floor, they're generally associated with these sections of the valley floor that are steeper, relatively steeper, say approaching 9%. The other thing we learn is that we can't really use theories or ideas from temperate climates to help explain how the valley floor is regrading itself, because we don't see a clear association with, say, channel steepness and the type of topographic expression at any one given location. So we need new ideas, new ways for trying to explain how a valley system that harbors polygons transitions to a channelized network system. We're able to obtain what we think is the oldest aerial photograph where we can clearly see the valley floor from the National Archives in Ottawa. That photograph, it dates from August 1959. And both of these photographs, this is from, we believe, 2019, although the exact date on this photograph from Google Earth is not, it wasn't given, but the prior date was 2017 in the photographic record. They're aligned perfectly in extent in terms of the bottom or the downstream end of the lake. And what I want to draw your attention to essentially is how conditions change from 1959 to 2000, we'll just say 19. At this point here, from here upstream to the downstream end of the lake, it's very difficult to see the expression of polygons or anything that may resemble a developing field of polygons. It's possible that they were there, but they were buried by surface sediments. We're going with the interpretation that they weren't really present in 1959. Contrast that with what we can see by 2019, where not only polygons developed, but then they were also dissected and essentially probably turned off by some set of flows that has started to develop a channel system. One thing that's similar between the two photographs is this section here of, we'll call it a gully or interconnected polygon troughs, perhaps. We see that present in both 1959 and 2019. We also see this, this very prominent seep tributary in both photographs. One of the main takeaways from this, if we believe the interpretation that polygons weren't present in 1959, is that in roughly 60 years, we can develop polygons over approximately a distance of about 400 meters, and we can also dissect and channelize those polygons in that 60 years. This is a relatively rapid rate of polygon development relative to mathematical and modeling theories, or I'm sorry, modeling studies that were done to test mathematical theories that tell us polygon fields or polygons may take on the order, say, of 50 to hundreds of freeze-thaw cycles. One of the other things we see that's different from 1959 to 2019 is it appears that we had a lake draining event sometime in that 60-year period. It's a former lake high stand is pretty prominent in this photograph I took of the valley. And over that, the difference there in lake elevation stand is a difference of about 3 meters of lake elevation. If you look really carefully in this 59 photograph, you can see this lighter band, and you can follow that around. If you compare that with this photograph and the photographs I took, it's pretty obvious that we had a lake draining event. This lake draining event could have been one of the, the key features or events that drove channelization or incipient channelization of this valley floor. So from these observations, one of the things that we can sort of bring the information together and speculate that channel development in Muskox Valley represents probably, or plausibly, I would say, a combination of rapid surface flow effects due to lake outburst floods, along with seasonal snowmelt floods and persistent flows from permafrost thaw, ground ice melt, and even water release from the fronts of solifluction lobes that are found up and down the valley walls. Okay, so the question that we are setting out to answer is, how does polygon terrain influence surface water routing and channel network development? Essentially, at this point, all I've shown you are observations from our time in the field and some data we collected, and we are analyzing that data following systematic processes, and we're trying to infer what could have happened in this valley from those data sources. But we can do a little more to try to directly address the question of how polygons may influence surface water routing, as well as our hypothesis of how polygons influence rates of channelization and landscape evolution. And we're going to do so by looking at some modeling we did of this region of the valley floor. We picked it because it has these multiple possible flow paths, and we wanted to see if those flow paths would factor importantly under the hypothetical case of releasing surface flows, say at the upstream end, and having water move through the valley floor and enter this region and then exit it. We basically want to see what the characteristics of surface flows may be in this region outlined in red. To do that, we used the 2D morphodynamic model to examine surface flow routing. The model is called Basement. We use version 3.2. It's developed at ETH. I picked this model because it's completely open source. It's very well maintained by the laboratory at ETH. They have annual model meetings where users can talk to other users about how they're using the model. And then the open source aspect means that anyone who has the skills can update and modify and release different versions of the model to address new technical challenges. For all of the modeling we turned off all transport of sediment. So we're just looking at the routing of water along the valley floor. This was the mesh I built for the region highlighted in red. The expansive region down here is associated with this wetland region where presumably flows can spill and follow any number of very small microtopographic gradients. And then the clear channelized region that you can see here is just following the primary polygon trough in the topographic data. So here's an example of output from the model. For this run, I ran a steady flow condition where I introduced 2.5 cubic meters per second of water at the upstream end of the DEM. And this image here is just showing how that water would be organized through the valley floor. And the result we're looking at right here is the water depth. So across the valley floor, the water depth ranges from, say, 0.1 meters to roughly 3 meters in depth. You can see clear spatial differences in how water is how water is organized in the more wetland type regions versus the polygonalized regions where polygons occur. The water is routed generally along the dominant interconnected polygon troughs, as we would expect. And in the wetland regions, flow is more diffuse as it spills out into this flat valley floor and follows microtopographic gradients. In the velocity case, we see similar differences between the wetland region and the polygon dominant regions. Primarily, we see higher velocities where water is restricted to follow interconnected polygon troughs at this flow rate of 2.5 cubic meters per second. And on average, the water velocities in the downstream direction, I should say, are a bit lower than what we see in the interconnected polygon regions. So the modeling sort of passes a straight face test that we would expect to see surface flows organized where we have interconnected polygon troughs with higher velocities, and less organized where we have these wetland regions we infer as depositional under present conditions with lower velocities. This was kind of cool. This result, I was excited by it because anytime you can run a model and get results that make basic sense, that's a good thing. But we didn't have a direct observation of this in nature until we went to Devon Island in 2022, the summer of 2022, July. Here's an example of active flow along interconnected polygon troughs that I found within the Houghton impact crater. This picture here is looking at this section of interconnected polygon troughs. You can see the people standing right here. That's the same folks. And in the image here, essentially flow is moving down topographic gradient along polygon troughs, and it's being routed down towards this more major water feature in the valley floor. And very close to here, I saw a similar thing. So in essence, what we see in the model domain, we saw in nature during the melt and thaw season on Devon Island. So we have both indirect and direct evidence that polygons that are interconnected can influence how surface waters flow across the landscape, and under the right conditions, with high enough velocities, large enough water magnitudes, we can actually start to shape these interconnected polygon troughs into defined channel systems or channel networks. That's the idea that we're working from. If we take a look at the modeling results in a little more detail, we can see clear differences in their probability distributions. In this case, we're looking at velocity. So here's the distribution of velocities in the wetland region. Here's the distribution of velocities in the polygonized region. And two things jump out. One is in the polygon region, we have a higher, or the occurrence of low velocities, or these sheltered regions, takes on more importance in the distribution itself relative to the more diffuse setting. This is similar to what we see in natural rivers in, say, temperate climates. And then we also see the extension of the distribution on the tail with these higher velocities that we can see in the results here, also consistent with what we see in more temperate river systems. So we can visually see differences in these velocities spatially, but when we look at them in a distribution sense, we can also see how they're different, and their differences make sense physically. Okay, so thinking about all of these results together, coupled with a lot of great work that's been done in Arctic settings around the world and high elevation regions, if we want to try to understand how channel networks are evolving or growing in the Arctic or high elevation regions as the climate continues to warm, one obvious thing we can do is we can take a look and remind ourselves of existing theories that are expressed or have been developed for temperate climates. There are any number of studies that we can look at. I cite some here that could be important. In general, they all say roughly, I won't say the same thing, but they point to a similar idea, which is as channels or as landscapes start to channelize and channel networks start to grow, we generally have these sort of nascent channel systems. There are many of them at the start because the landscape hasn't yet organized according to its water budget and sediment budget. Over time, these discrete channels grow into a developing channel network system. We lose some of these discrete systems. They merge and coalesce with their neighbors. And over time, we lose even more as we grow things that start to look more like drainage basins or interconnected or channel networks in general. The key problem with all of these theories and why we cannot just apply them to cold regions or cold environments is because we do not know how sediment transport, erosion, and deposition occurs when the ground is frozen or partially frozen. And this is relevant for these smaller stream systems, which will be largely what outlines these nascent or these developing channels that evolve into a network. When these things, they go dry or partially or mostly dry at the end of the season so that their beds can actually freeze through as opposed to larger river systems that maintain flowing water. They have an ice lid on it. Their dynamics are very different than some of the systems that we're thinking about in the Arctic today. So we need to answer this question of how does frozen sediment or partially frozen sediment erode during the evolving thaw and melt seasonally. To put some ideas to this, we did some basic calculations to identify the role that different heat events or thermal events could play in development of thaw depths on the bottom of channels or evolving channel networks, and how that may relate, say, to a relatively coarse particle size on beds that are alluviated or at least are composed of, say, gravels and cobbles. And essentially what we see is that, say over the course of 10 days, if we have a +5 C temperature bump from freezing, we can evolve along this type of thermal trajectory where, say, after 10 days, we have thawed the bed underneath the channel to a depth of roughly 2.5 D90 particle sizes. Essentially what we're saying is after 10 days, if we have a 5 and above zero temperature change, we can probably start to thaw the bed enough where active bedload transport can start to occur. However, if we kick that up with a 15-degree event, we can see that we can start to thaw sediments under the bed to even greater depths at more rapid rates. And the key essential thing to take away here is that the sequence and the magnitude of these different thermal events or these heating, these air temperatures above the bed, that's going to dictate how and if we can erode these evolving channel networks seasonally. And the expectation would be into the future, as air temperatures in the Arctic continue probably to be amplified for some period of time, that we can expect this to be probably a fairly significant driver of evolving channel networks. Muskox Valley is not the only place on Axel Heiberg nor Devon Island where we see polygons playing a direct role or directly influencing the development of channelized networks. Here's an aerial photograph where we show roughly 45 different locations where we made observations similar to what we see in Axel Heiberg, or I'm sorry, in Muskox Valley. And then on Devon Island, I just offered this photograph in the middle of the Houghton impact structure, where we can see polygons forming at the heads of these tributary channels that are coalescing into this larger stream that then flows down into the Houghton River. So if we look hard enough, we can see similar types of processes occurring at many different places across at least the Arctic. So some concluding thoughts, just wrapping it up. Then this mainly field-oriented exercise with some calculations to support it and modeling to support it. We believe that polygons can exert a strong control on how channel networks develop, how channel networks develop, and then how water is organized at the landscape scale here, with the example being this sub-basin, which we called Muskox Valley. Valley floor channel development can be semi to discontinuous in space, and it seems to be driven by thermal and mechanical erosion. And presently, we really have no idea how to incorporate the thermal erosion effects into existing theories, say, of how sediment is transported along river bottoms, and particularly in evolving channel networks. Drainage development theories for runoff-dominated systems are presently not directly applicable. We can lean on that style of thinking, but there's some work we need to do to expand those theories for cold regions. And essentially, immediately, we need to better understand how channel networks develop in paraglacial systems due to climate feedbacks, and most importantly, how the thermal state of the channel bed and the relation to runoff timing holds together, probably in a probabilistic sense, to set how new channel networks form and essentially how new drainage basins come to be in Arctic and high elevation settings. Looking ahead, some work that we're doing right now to address these questions that extend our recent publication is we've built 2 different experiments in the lab. I tried to get photographs to show you all of what we're up to, but with the snow last week, I could not actually get into the lab. But we have a big freezer where we're growing polygons presently. We essentially turn the freezer on and off, on and off. We have an ability to sort of control the humidity in the freezer. We apply water, so we control the water budget, and we can see that with some regulated freeze-thaw cycles, we can start to grow things that look like polygons. We also have a small flume where we are putting sediments into the flume, filling it with water, freezing it, taking it out. Then we're running water over that, and we're looking at how the thermal state of the bed affects the rate of particle entrainment, and then how that affects, say, the local topographic characteristics of a particular region of the flume. So that's it. Thanks for your time and interest. And I'd like to thank the folks in the Inuit that we work with, particularly in Resolute Bay, where we've developed a relationship. And I'm happy to say that this coming field season, when we go to Devon Island, we will have a member of the community in Resolute Bay, Devon Manick, join us so we can start to learn from each other in this idea of how the landscape in the high Arctic is responding to climate change and Arctic amplification. So thank you.
And, did you hear the applause, Shawn?
Yes, thanks. I appreciate it.
Okay. Okay, any questions? Sally, you have a question? There's a microphone coming to you. Number 1? Is it number 1? Stage microphones? Or wireless microphone? Handheld 1?
Yep, handheld 1.
Hello. Hi, it's me. Hi, Shawn.
Hello.
Thank you so much. Forgive my ignorance, but how does a polygon get made? Can you just describe how that works?
Yeah, this is a question that has been the focus of a lot of research in the past. Essentially, the basic idea is you have a substrate of a certain type, and as you enter the winter season or the cold season, and that material starts to freeze, you put stresses on the ground so the ground contracts, it essentially shrinks, and that starts to form cracks in the ground. Essentially, when you get these cracks early on, a lot of these cracks are orthogonal in nature. They're, say, at 90 degrees to one another, or you have a bunch of dominant cracks that head off in various directions. As you enter the next melt season, those cracks are thought then to be filled with water. They hold this water through the summer melt thaw season. They enter the next cold season. That water freezes, and so as the ground contracts and the water in the crack freezes, this puts more pressure on the land shrinks or contracts even more, and some of it gets jacked up. This occurs over more and more, or this occurs, in the future over many different freeze-thaw cycles. New cracks form, and then eventually you get this landscape that has this pattern of polygons in it that then harbor a lot of times ice within the cracks themselves. What I can tell you is we dug a lot of trenches across polygon troughs in Axel Heiberg Island in 2019. We did not always find ice in the say primary troughs where the cracks were obvious, and sometimes we did. But the prevailing theory is what I just described. Hopefully that made sense.
Yeah, I think it did. Any other question? Peter, I think you're up the front.
The models you're describing are sort of quasi-steady state. The topography reminds me of what I've seen in the I don't know, desert southwest of the United States. Very arid, and there the primary erosion action is catastrophic. It is an event, that causes something to happen, and then you get a sort of return to steady state. And you mentioned a lake failure. How did that sort of affect how you were looking at what was going on in this valley?
Yeah, that's okay, great. Yeah, that's a great question. Yeah, very similar, I agree. Essentially, the only vegetation that we saw in Muskox Valley is, say, within these wetland regions. You can see it's obviously green in the photographs. This was that seasonal, these were seasonal grasses that grew to, say, heights of between 5 and 8 centimeters. Over a lot of the rest of the landscape, it was just rocky. And yeah, I agree with you. When we walked the valley from downstream to upstream, we didn't actually realize that the lake was at the upstream end of the valley until we got there, because our helicopter approach was pretty far east of the valley, and then we flew directly up valley. So when we were walking up valley, it was, I would say, confusing why we were seeing these interspersed sort of channelizing sections with these more wetland type sections. And then when we got close to the valley or to the lake, we saw this very prominent, I would say moderately deeply incised channel system. And then when we saw the lake and we saw this sort of bathtub ring that would indicate a lake draining event, then things started to make sense. I agree with you. Probably, or a plausible explanation is that a lot of the channelization we see in Muskox Valley is related to this lake draining event. But because we have seasonal melt and thaw, and we don't have a strong understanding of what the precipitation record is, say, over the last 60 years in Muskox or near it, because the closest climate station is quite far, it's possible that seasonal thaw and melt has also played a important role in driving channelization. But my gut instinct leans in the direction that you're thinking. This flood was catastrophic. It really drove a lot of the erosion we see today, and now it's evolving much more slowly.
And sort of to follow on from that, are we not expecting more and more occasional catastrophic events, the slump events causing perturbations in the landscape? So really modeling the after effect of an event. I mean, you need to understand the quasi-static stuff, but to really get a model that's going to predict the changes in the landscape, you need to understand the catastrophic events and the follow-on from them, right?
Yeah, I would agree with that idea. Certainly. Yeah.
It's a more difficult problem. Enjoy it.
Okay, thank you. Thank you very much. Non-steady state, non-equilibrium systems.
Another question coming to you.
Yeah, thanks, Shawn. Actually, it's a similar question, but it's not necessarily catastrophic. It seems to me that quite a few of these erosional events would have been triggered by annually, just by things like the timing of the major melt events early in the growing season, or single precipitation events that may have been episodic during the short summers, and that those in and of themselves could explain or could help to understand why some channels are eroding through right now and others aren't. Say, for example, in your distributional situation there, where you've got more than one channel, which is kind of unusual in many dendritic networks, and but it's relatively common in drainage from glacier, periglacial environments with massive diurnal fluctuations in water regime and so forth.
Yeah, I would be dishonest if I pretended that we couldn't plausibly explain it along those lines as well. Like, we're dealing largely with an absence of information here. So we're trying to piece the story together from as much environmental information as we can reconstruct. And to your point, I would say that when we look at the 1959 photograph and we see, from the photograph, what looks like a connected and developing gully system, this probably is more akin to what has been reported, say, by others, Fortier and Godin, and relates to the sort of watershed development theory by Tom Dunn, where essentially we get seepage flows at the head of this gully system and at the head of these small little peak gullies that are forming off the main gully, and those seepage flows are driving seasonal erosion of the head of that gully, and through that we get advancement. And then we layer on top of that, I would say, at least one flood event that's caused by a lake draining event. So we get this combination of events that are driving the expression of this evolving channel network in Muskox Valley. And so at this point, because we have no way to model how substrate on the bottom of evolving channels within coarse substrate erodes during different flow events, because it could be frozen or partially frozen, we don't have a lot of ways to test different ideas at the moment. This is why we're running the laboratory experiment in the mini flume, so we can try to develop the theory we need, at least to test drive some of these ideas in a preliminary way, where we say, try to model the entire valley floor itself at different initial conditions with different types of contributions to seasonal flows. We have hydrology models that are capable of doing that today, and then systematically start to test different ideas. I would say we're 3 to 5 years away from that at a minimum. But I agree with your point. We can't rule anything out at this time.
Go ahead.
Hi, Shawn. You mentioned that the valley is 3,000 years old, and the picture in 1959, as you pointed out, doesn't show much in the way of polygons. And what is your concept of what this valley would have looked like for most of those 8,000 years? Does it go back and forth between, like a movement back and forth between polygonal development and are the polygons formed during the warm periods, or relatively warm periods, and then if everything is frozen up solid, developed system in the creek? I don't know. I just wanted to know.
Right. Yeah, that's a really good question. Yeah, I mean, depending on how long the valley itself has been present in the topography of Axel Heiberg, it would seem to me to make sense, depending on the severity of warming during interglacials, that you could get sort of the development of polygons when the conditions are right. There are some ingredients that are necessary. During these warm periods, the landscape starts to change, and then we enter another, if I'm reading your question correctly, so you can correct me if I misunderstood it. We move back into a cold period, the landscape sort of gets rewritten because other processes are dominant, and then it starts to change again as we say the climate warms up and we enter another interglacial period. It seems plausible to me. I would love to know the longer term history of this valley. We have some plans to try to do that. Whether or not we'll get funding to try to piece together a longer term history, I'm not sure. Yeah. But I guess related to your question, one of the things that interests me sort of in a storytelling manner or an intellectual manner is that if we fast forwarded 300 years from now, maybe even longer, to a time when the polygon record itself has been erased from the valley floor, and we have a, say, more mature alluvial channel system that exists in Muskox Valley, if a scientist went out there at that time, would they even know that polygons were important in the development of the channel system as the landscape, as the climate started to warm. I think about these things, say, at the margins of the Cordilleran ice cap, where we know polygons were present at much more southerly extents. And how did those polygons play a role in the development of river systems we see today? There are some folks at the University of Minnesota that are starting to look into these ideas at a much larger scale, and they're sort of tending in a similar direction as that idea.
Okay, one more question.
Yeah, my question is about how far away is this Muskox Valley from the ice cap that you showed in the broader overview, and is that drainage system actually connected to the ice cap at all?
Yeah, it's a good question. Presently the ice cap, the closest edge of the ice cap is about 2 kilometers from the valley itself. There is a prominent ridge right here, and that ridge extends all the way up to roughly here that separates the valley from the ice cap. So how long ago was the ice cap flowing down Muskox Valley? Not sure. Maybe a couple thousand years ago. It's difficult to discern because there just hasn't been much work up here to piece together a more detailed history of the post-glaciation period. This is, though, one of the things that we'd like to look into because we're going back to Axel Heiberg in the summer 2025. This summer, we're going back to Devon Island. So it's a good question. Yep.
One quick follow-up. There must be, obviously, since you have that ice cap, there must be places where there's a lot more water available, drainage directly off the ice cap, and that could obviously be something that climate change could be increasing.
Yeah, I agree. I mean, most of the ice on Axel Heiberg is cold based, so it's frozen to the land. So that things work a little differently, and that's why a lot of the valleys you walk in on Axel Heiberg, there's very little expression of topography. It's very smooth. It's bedded in gravels and cobbles. So the system, Axel is a bit different than, say, Devon Island, where there's less cold-based glaciation on the west side of the island. And that plays a role in sort of the initial conditions that one has when sort of incipient channelization can start to occur. My best guess is when the Mueller ice cap receded out of Muskox Valley, most of the valley floor was quite smooth, and it wrapped up the valley walls, and it was bedded in fairly coarse material, gravels and cobbles.
Okay, well, thank you very much, Dr. Shawn Chartrand, for your very informative lecture.
Thank you.